The root locus and the sketching of the root locus is a really good example of a topic in this class where practice does help quite a bit. What we're going to do here is a long activity where you're just going to churn through several different increasingly more complicated transfer functions, loop transfer functions, and we're going to draw the root locus. So just practice all those sketching rules. What I'd recommend is that just to get used to everything, I would go ahead and apply all 5 rules and see what they all have to say. What you're going to notice is that many times you can draw the basic diagram even with just the first 3 rules. And so those more complicated rules don't even need to come into play. But I do recommend that you go ahead and go through it just for the sake of completeness and to better practice these rules. So in the first 2, what I'm doing, or the first one, I'm essentially providing you with a transfer function of the system and then explicitly saying what the controller and maybe the feedback loop transfer functions are. And then from there on out, I'm really just giving you a loop transfer function, which is the product of G, D, and H in the model that we looked at in the beginning slides. And so, for example, the second one, just as an example, could be studying actually the same system, open loop system, but now with a controller that may be like a PD controller. And so this S plus 1 is one where the proportional control gain would be 1 and the derivative gain would also be 1. So it's just an example of how you might construct this loop transfer function, but there could be a variety of other ones. So go ahead and go through. I'll try to go through the solutions nice and carefully, and again, apply all 5 rules, and then sketch out the root locus. Okay, so in this first example, we're going to be taking a look at the double integrator plant. So this is an example of a transfer function that's still simple enough. So if you wanted to, you could go ahead and create the denominator polynomial and literally find the roots. And we did this in a previous example in the prior slides, where essentially we would, so this is the denominator, and we're setting that equal to 0, and so that would be finding the roots where s is equal to 0. And so this is a way of literally finding what the root locus would be by finding where all the roots are parameterized by the value of k. So we don't want to do that because what you're going to see is that that becomes more and more complicated and more difficult to do. So what we'd like to do is rely instead on the sketching rules, but it's always good to know where this is coming from and how to actually compute those analytically. Okay, so rule 1 says that tells us how many branches of the root locus we're going to have, and so those correspond to the open loop poles. So in that case, we have 2 poles, and they're both located at s is equal to 0, so they're located at the origin. And so I'll draw that with 2 overlapping x's at the origin, and there are no zeros. So there's no nothing in the numerator, no terms in the numerator. And so what that means is we're going to have 2 branches, and none of them go to zeros because we don't have any zeros. So the second rule tells us that the root locus is on the real axis to the left of an odd number of poles and zeros. And in this case, we have just 2 stacked up here at the origin, and so that means that there's nothing to the right of it and there's nothing to the left of it because there's never an odd number of poles or zeros. So it means it's actually never going to be on the real axis. So that already tells you that. Since we have no zeros, so m is equal to 0, then that means that both of these branches need to terminate at asymptotes. And so we can calculate where those asymptotes are. So the formula for the asymptotes goes like the sum of the poles minus the sum of the zeros. And in this case, both of our poles are located at 0, and we have no zeros, so that's the 0 there. And we're going to divide by n minus m, which is 2, and so that means that our asymptotes are at 0. So our kind of asymptotes here are at 0. We could draw those in. And so then we're going to compute the angles that those asymptotes are going to be. So I just drew that in, and that's a little premature. So in this case, we just know that they're centered at 0. So now we have to figure out what angles they are. And so plugging that into this formula, we're going to do 180 plus 360 times L minus 1 over N minus M. N minus 1 M is 2. And L goes through all of the different N minus 1 M options. So it goes 1 and that goes 2. So when L is equal to 1, this term is 0, and so we're just left with 180 divided by 2, which gives us 90. When L is equal to 2, we get 360 times 1 plus 180, so that's 540, and then you're going to divide by 2, which gives us 270. And so 270 is either all the way around, 3/4 of the way around the circle, or it could be back by 1/4. So 270 is the same thing as minus 90. So now we know that it's centered at 0, and these asymptotes are going up at 90, and they're going down at minus 90. All right, so at this point, you could probably already draw this graph. It is possible in the future, we'll see examples where, for example, you could have departure angles where the root locus might emerge out at a different angle, or it could emerge out at a different angle. In this case, it doesn't do that, so these are not true. So one way to see this explicitly is to go ahead and look at the departure angles. So we can measure the departure angles of these poles, and so this has multiplicity 2. So we have to use the formula that has the multiplicity, where Q here is equal to 2. And in this case, there are no other poles. Well, the other pole is the other 0 pole, and the angle to that is kind of defined as 0. So it's sitting on top of each other. So its angle is pointing at 0. And then there are no zeros. So this term is 0. And then the rest of that formula is just minus 180, and then minus 360 times L minus 1. And again, we just plug in 1, and then we plug in 2 here. So when it's 1, then it's just minus 180 times the 1/2 that we have here. And that gives us the minus 90. And then when L is equal to 2 here, then this is minus 180 minus 360, which again is minus 540. Multiply that by this 1/2, and you get the minus 270, which is 90. So this means that these branches are going to be departing at minus 90 and at plus 90. So it means that right emerging out of these poles, these are going to be exiting at plus and minus 90. And so that means that the arrows along this root locus are going to be pointing up along the positive imaginary axis and down along the negative imaginary axis. If you wanted to, you could go ahead and use Rule 5. I didn't put it down here, but what Rule 5 says is that at a point of multiplicity, and technically these 2 poles at the origin are a point of multiplicity, you could again calculate how the root locus splits, and it splits at theta is equal to 180 plus 360 times L minus 1 over Q, and in this case we have multiplicity 2 here. 2 branches are splitting, so now L is equal to 1 or to 2. And you notice that this is exactly the same formula that we have here, and so we're again going to get these angles of 90 degrees and minus 90. And so that's yet another way to determine the departure angles here. In this case, we're explicitly, with Rule 4, calculating the departure angles. In Rule 5, what we're doing is we're actually seeing the angles at which the root locus splits at a point of multiplicity. So this just helps us essentially get at the same values, but again, useful to kind of go ahead and go through those computations for all of those. So since the poles emerge out of the open loop poles here at plus and minus 90, and then we know that the asymptotes that they approach as k goes to infinity also are at plus and minus 90, the simplest thing for them to do is just go straight along this imaginary axis, which is in fact what they do. It's possible that you could believe that something else happens in between, that they somehow diverge and then come back, but there's no real reason to do that. And remember, these are sketching rules, so these don't tell you absolutely everything about the the behavior of the system, but you just interpolate based on experience, which is what you're going to get through these activities, as well as just the simpler solution dominates. So again, this is our solution. Now this is what's exactly on the slide, and so this maybe shows just a little bit more clearly how we compute all of that stuff. And one final thing to note is, again, that if we solve this, we could just say that S is going to be equal to the square root of minus k, which would go like I times the square root of k. And so this plus or minus, I guess, yep, plus or minus this. And so what that means is that this is really showing you that as k increases, it's literally going along this imaginary axis in both positive and negative directions. So again, you can find the roots this way, but eventually that's going to be too complicated, which is why we go to these sketching rules. All right, so let's take a look at our second looped transfer function. So in this case, what's changed is that we have a numerator, and that numerator adds a 0. And so in this case, again, we have two branches of the root locus, and they start at the double pole at 0. We have a 0 in this case, and that 0 is located at s is equal to -1. And so that means one of our branches, 1 out of 2, approaches that 0. So if we go ahead and draw our pole 0 diagram, we're going to put our double poles there, and we can put our 0 at -1. All right, so now we actually have something interesting to say from rule 2. So to the right of these double poles, there's no, it's to the left of, so this region over here in the positive real axis, this is to the left of 0 poles and zeros, so that's even. So that doesn't, it's not going to be on the real axis here. In between here, between the double pole and -1 on that interval, it's to the left of an even number of poles and zeros. But then once we get out to past -1, then this is actually to the left of two poles and 1 0, so that's an odd number, cumulative, which means that the root locus is going to be on this axis, the real axis, to the left of that 0 value. So that's what rule 2 tells us. Rule 3 says that, okay, so we already know from rule 1 that one of the branches is going to converge to this 0 at -1, and the other one has to go somewhere else. And so we've already actually figured this out. Because of the behavior that we're seeing here, we're already seeing that the root locus is going to be on the real axis to the left of -1, which means that we are going to have a branch that's going to go off to -infinity over here out at this angle. And so we can just go ahead and confirm that using rule 3. We see that n minus m is 1, so we're going to have one asymptote. And in this case, it's going to again be the sum of the poles. The poles in this case are both 0, so that gets that. And then we subtract away the value of the zeros. And so in that case, we have 1 0, and it's at -1. And so we get minus a -1 over n minus m, which is 1, which gives us 1. And so that says that the center is going to be at 1. So in this case, you figure out where 1 is over here, and so that's going to be alpha. That's alpha is equal to 1. And so what is the angle? The angle in this case, when we go ahead and compute that, if you wanted to write down the formula, is simply just 180 plus 360 times L minus 1 over 1, because 1 is n minus m. And in this case, L is simply just 1. So that means this term goes away, and you're just left with 180. And so that means that the asymptote is centered here, and the asymptote goes out at 180 degrees. And so that's the same thing as what this branch here is going off to -infinity. All right, so now we go to departure and arrival angles. When we have our departure from the poles, our calculation is quite similar to what we did before. The only difference is that when we calculate the departure angles, now we actually have a 0 value. And in this case, the 0 is here, and for it to point at the poles at 0, so we're looking at the departure angles of the poles, it's going to look, and it's going to look at this angle, and that angle to look at those two poles over here, that angle is going to be 0. And so here we actually have 0 degrees. It's not a 0 because we don't have zeros in this case. It's actually, we have a 0 and it's located at -1, and to point at the poles at 0 located at the origin, then that angle is 0 degrees. Then we have, again, one of the poles looking at the other one, which again is just the angle 0. And then we subtract off -180 and subtract off -360 times L minus 1. And in this case, we have 2 of those poles, and so we have a 1/2 there. And so that same calculation, essentially the same value as what we got before, since this doesn't contribute, and we get -90 and +90. So that means that out of these poles, we're going to be departing at plus and minus 90. Now we take a look at the arrival angle at this 0. So again, we actually already know this information because we had rule 3 telling us that it's the branches to the left of this on the real axis. So we already know that there is a branch that's approaching this 0 from the left, but we can go ahead and confirm that. So the arrival angle, the way that we could compute that, so this has no multiplicity. So all we have to do is, it's going to be the sum of the angles from the poles to that 0. Subtract off any other zeros. We don't have any other zeros. So again, let's just write this out. So this would be the sum of, say, phi I j, where j in this case is going to be 1. And then we're going to subtract off the poles, the zeros, any other zeros. So this would be the angles from any other zeros to the 0 that we're interested in. And then plus 180, and then that's it. So in this case, we don't have any other zeros, so that term is not present. And in this case, we have 2 poles. They're located at the origin. In order to look at this 0, you have to observe an angle of 180 degrees. And so that's why we add in 180 degrees. And since there's 2 of these, we get 2 of them. And so when you add this all up, you get 360 plus 180, which you can get rid of the 360. It just kind of spirals around. And so the angle that it's pointing is 180. And so that's the same thing as saying that the arrival at this 0 is simply coming from the left. And that's what we already knew because it's on the real axis to the left of that 0. All right, and finally, what we're observing now is we have departure out at these poles at plus and minus 90, and then the branches go to the right, so they go towards this 0, and they also go back to the left here. And so what that means is that the simplest way for these to get there is for these to make it over here. And so one of the really important things to keep in mind is that the roots that we're talking about, these, whenever the root locus is off of the real axis, that's because the roots of the denominator polynomial are complex, or have at least some aspect of them that are complex. And so that means that they have to occur in complex conjugate pairs. So that means that at some k value, so k starts at 0 and we're at these open loop poles. As k increases, you're going to move along the root locus. And so at some point in time, you could stop. And so if you stopped right here, that's a complex pole. That's a complex closed loop pole. And the whole idea there is that those complex closed loop poles need to come as complex conjugate pairs, which means that there needs to be another pole down here that is its complex conjugate as the root of the denominator polynomial. And so for that reason, the root locus is always symmetric over the real axis. So you're always going to have these ellipses and circles and other things that essentially are flips of each other over this real axis. So that's an important thing to keep in mind. So again, because the poles had to leave here and we knew that they had to end either at the 0 or out at infinity, that means that these branches had to make their way here. And so right now what we're interested in doing is figuring out what the angle of approach is right here. And so what we're observing is that we have two branches that are meeting. And so that's something that Rule 5 tells us about, which is when multiple root locus branches come together. And so in this case, we have two branches coming together. And so if we plug that into our formula, we have 180 plus 360 times L minus 1 over how many branches is 2. And so then you plug in 1 and you plug in 2. And what you're going to notice is that you're going to keep doing the same computations over and over again. And so in this case, whenever you've got 2, either up here or for the angle of the asymptotes, or down here for the multiplicity, you're going to keep getting the same value. So you're going to be able to compute these pretty quick, pretty soon. So in that case, you get plus or minus 90. And so what that means is whenever you have two branches coming together, they're going to come in and emerge at angles of 90. And so it means that this is actually, when this comes around, it's actually going to come in and it's going to be perpendicular as it comes into the real axis. So that describes everything that we have here. But there is a little bit more that we could say if we go beyond our sketching rules. Okay, so now I'm just going to show you the solution that I have in the notes. So the one thing I do want to point out, again, we don't want to continue to do this because this is going to get too complicated. But if we were to go ahead and form the denominator polynomial and explicitly solve for those roots again, which again is kind of against the whole idea of doing root locus, but it's useful to kind of show how this works. So if we have this polynomial, this is a quadratic, and so we can solve it using the binomial theorem here. And so the roots look like this. And so this means that, first of all, they're always going to be negative real parts. So that kind of indicates the fact that nothing is over here in the positive real side of the plane. And then what we're observing is this discriminant becomes 0 when k is equal to 4. So when k is equal to 4, this value here is 0, and whenever k is bigger than 4, that becomes a positive number. And so when this discriminant is positive, the square root, you can go ahead and take the square root and get a real number. And so once k is bigger than 4, you're actually getting real roots. And so that's what you're seeing here on the real axis here. That's the same thing as getting real roots all the time. When k is less than 4, what we're getting is this discriminant to be negative, which means that you're going to get complex roots. And so that's why we keep getting complex conjugate pairs. So k is equal to 0 starts here. As you increase k, you get bigger and bigger and bigger. And then once k gets to 4, that's exactly when these two branches merge together and you get a double root. And that's what happens here. When the discriminant is 0, you just get a double root at minus k over 2. And so in that case, what ends up happening, so minus k over 2 in that case would be minus 4 over 2, because k is 4 in that case. And so that's minus 2. And so that's a way of figuring out where exactly these branches come together. Our sketching rules don't tell us that, but if you wanted to dive into this deeper, you could just kind of understand how the sketching rules are kind of giving you the same behavior that you're getting from these roots directly. And so obviously this example is quite similar to the previous one. In this case, we just have this extra 0. And so one of the interesting things is we had this root locus that was essentially on the imaginary axis before. And so one of the things you can do is you kind of imagine that by putting this 0 in play here, it pulls these down. You pull these down so that they're no longer on this kind of marginal stability imaginary axis line. It actually pulls them into the left half plane, which helps. So by putting this PD controller, particularly the derivative part, which gives us the 0 here, that's what's actually pulling us down like this and making it more stable. So those roots becoming more into the left half plane is important for that stability characteristic. Okay, so now we're starting to see some more complicated examples. This is still within the realm of being able to form the denominator polynomial, but clearly now that it's a cubic, it's going to get difficult to solve. So we're no longer going to be able to leverage any of those analytic techniques anymore unless we get particularly lucky. So the idea is to rely on our sketching rules. So let's do that. So in this case, we have now 3 poles. So we've essentially added a pole at minus 12. So we still have 2 poles at the origin, and then we have a pole out here at minus 12. We have a 0 at minus 1, just like we did before. And so what we know is that we're going to have 3 branches, and they're going to start at 0 and at minus 12. And one branch is going to converge to the 0 that's located at s is equal to minus 1. And so then we can move on and calculate where the root locus will be on the real axis. So just like before, this is to the left of the poles at the origin. That's an even number. And then once you cross over to the other side of the 0 at minus 1, now that's an odd number, and so it's going to be on the real axis throughout this entire interval. But then once we reach minus 12, there's going to be an even number, so it's going to be 3 poles and 1 0, so it's an even number, and so it's no longer going to be on the real axis after minus 12. So that means it's going to be on the real axis between minus 1 and minus 12. So we had 3 branches, and one of them converged to the 0. We can already kind of see that here, so we already know that it's going to go like this. So then the question is, where do the other 2 branches go? So we have n minus m, which is 2 asymptotes. So then the formula here is we're going to take the sum of the poles. So one of the poles is at minus 12. The other poles are at 0. So it's just going to be minus 12 plus 0 plus 0. And then we're going to subtract away the sum of the zeros. And the sum of the zeros is just minus 1. And so that's divided by n minus m, which is 2. And so that gives us minus 11 halves, or minus 5.5. And so that means our asymptotes are going to be centered somewhere around this value, which is minus 5.5. And then the question is, what are the angles? The angles, again, as soon as you see this 2, you're going to keep being able to calculate out these angles very quickly. So again, with n minus m is 2, we just get plus and minus 90. So our asymptote looks like this. And so now the question is, what does it look like? So we would like to know departure angles out of these poles. We can go ahead and calculate the arrival angle of this 0. Again, we already know it, but it's worth double checking. Again, we already know the departure angle out of this pole at minus 12, but again, it's worth checking. So the departure angles out of our poles at the origin, so they have multiplicity 2, are zeros. We just have one of them. Again, it looks at the poles at angle 0, so that's where that comes from. And then the rest of the formula comes down like this. That again gives us plus and minus 90, just like we did before. So these are going to be departing out at plus and minus 90. If we want to look at the arrival angle of this 0, then the sum of the poles. So again, these poles at the origin look at an angle of 180. The pole at minus 12 looks at an angle of 0 degrees. And so that gives us 2 copies of 180, a copy of 0, and then we also get the extra 180 that's in the formula. And so again, this gives us 180, which again confirms the fact that this is entering from the left here to approach the 0. We can calculate the departure angle out of this third pole, which is at minus 12. In that case, we're going to measure the angle to this pole out at minus 12 from the 0. So that's going to be an angle of 180. So that's where we get this 180. And then we're going to subtract away the angle from the 2 poles. Again, these are also 180. So you get 2 copies of that. And so when that's all settled and canceled out, we get an angle of 0. And so that is indeed the angle that the root locus departs out of this pole at minus 12 because we know that this goes in this direction and then heads in that direction. All right, so these are emanating out here and emanating out here. Just like before, we know that these branches need to go along this asymptote. So at some point in time, our root locus should be going out along this asymptote. And there are a variety of different ways that this can happen. And so one of the things I'd like you to try is an in-between case. So right now we're going to do this pole at minus 12. We're going to look at another case, which is at minus 4. And then I'll let you work the case at minus 9. And you'll see that you get different behavior, even though the sketching rules are a little bit vague in how all this happens. So if it did decide to meet up like what happened before, so where this would come in, again, because these are complex conjugates, this has to be symmetric. So if this happens like this, then by the same logic of how we calculated before, we get this, by rule 5, we get the angles approaching here at plus and minus 90. And in that case, the way this would look is we would have these two branches leaving the origin, coming around in this kind of circle, and then one of them entering the 0, and the other one coming in and meeting this other branch that's coming from minus 12. They meet up, and then they split and go up at these asymptotes. Again, the sketching rules are vague on exactly how this works. It's not immediately clear whether they would meet here or they could meet on the left-hand side of this minus 5.5. And what we're going to see is that the location of this pole actually affects exactly how everything happens here in the middle. And again, the sketching rules are a little bit vague, but again, because we have computational methods like MATLAB, we can actually check what this root locus looks like, and we can see that indeed, in this case, this is the way this looks. So again, here's just the final solution. Again, if you really wanted to, you could numerically find these values using MATLAB, and so these are the values where these enter. I think on the last slide I didn't explicitly mention, in this case, two branches are coming together, and so we calculated the angle of 90. When this happens, two branches are also coming together, and so by the same math, these would happen at 90 degrees, just like before. So it's two branches coming in and two branches leaving. So in this next activity, we're essentially solving the same problem. What's happened is that we've now moved this pole closer, closer together. And so now it's a lot closer. So this is going to be on a slightly different scale as before, but this is going to be now we have a pole at minus 4, and now we have two poles still at the origin. And we still have this 0 that's located here at minus 1. And so by the same logic that we had before, we know that it's going to be on the real axis between these points, between the 0 and the pole at minus 4. We know that we're going to have asymptotes because n minus m is still 2. We're still going to have plus and minus 90 asymptotes. The location of those is going to change. It's going to be minus 4 minus the sum of the zeros here, which is minus 1. So that gives us a different value. What was minus 11 halves before is now a minus 3 halves. And so that means that's just going to be a little bit beyond, our asymptotes are just going to be a little bit beyond our 0 here. And so they're at plus or minus 90. So this is where alpha is. All right, so we can again go through this very similar calculations for the departure and arrival angles. Again, in this case, nothing has changed, so I'll just go through those and make sure that, that this makes sense to you. We have departure angles at plus or minus 90. We have the arrival and departure angles that we already knew about. So that means that this is heading to the right. This is also heading to the right into that 0. We know that these are coming out at plus or minus 90. And in this case, again, this is where the sketching rules get a little bit vague, but what happens is that this directly goes out along these asymptotes. And so there is no point of multiplicity. So this is something that the sketching rules do leave out. And so if, say, on a quiz, or you would not be penalized by drawing this figure for the previous activity or vice versa. But using MATLAB and numerical tools, we can actually calculate out all of these. And so again, the really important thing about understanding the root locus is, and being able to sketch it, is so that you can kind of understand how adding a pole or a zero affects the overall root locus. So it's not necessarily to get the details correct, but as you're working in MATLAB, you can think about adding a pole or a zero and understanding how that's going to change things. So like I said before, we've seen this example at 4, we've seen that example at 12, and now what I encourage you to do is go ahead and do this again for the value at 9, and what you'll see is that that's this kind of critical boundary case where right now at 4, these are going directly to the asymptotes. What we saw before is that those are going first to the real axis and then out at asymptotes. And so this is this kind of critical case where any value pole less than 9 gives you something that looks like this. Anything greater than 9 gives you something that looks like what we saw before. And again, this is just my solution showing you what this root locus looks like. All right, this last activity is a doozy. So in this case, we've got a large transfer function here. So we can see over here that we've got a 0 and a pole, and then we have 2 poles at the origin, and then we've got some complex poles and zeros. And so once you kind of work this out, you'll see that you've got poles, 2 of them at 0, 1 at minus 12, and 1 at a value of minus 0.1 plus or minus 6.6i. And then we've got zeros at minus 1 and very close to those poles, minus 0.1 plus or minus 6i. So if we were to draw this out, we have 2 poles at the origin. We have a 0 at minus 1. We have a pole out here at minus 12. And here at 0.1, you've got poles and zeros. The poles are a little bit further out. So the poles will be slightly further out than the zeros, and these are complex conjugate pairs. So it's going to look like this. So what you're going to notice is with these complex conjugate pairs, because there's 2 of them that come together, they're not going to really affect rule 2 at all. They don't play a role. So again, by the same logic, it's going to be off of the real axis between 0 and minus 1, and then it'll be on the real axis from minus 1 to minus 12. Again, those complex conjugate pairs don't really change anything. So calculating the asymptotes, we know that we have, in this case, 5 branches, and they're going to head to 3 of those. 3 of those branches will head to the zeros. So there's going to be 2 remaining ones that are going to go to asymptotes. And so where's the center of those asymptotes? That gets a little bit more complicated. We're going to sum up all of the pole values. So that's minus 12, minus 0.1 plus 6.6i, minus 1 minus 6.6i, and then the 2 poles at 0. And so the nice convenient thing about this is that these complex terms are definitely going to cancel. And the same thing happens out here when we look at the zeros, and that leaves us with a value of that asymptotes at minus 11 halves. And then we calculate the angles, and again, since there's just n minus m is 2, we know that's going to end up being plus or minus 90. So there's going to again be an asymptote somewhere in here, and at minus 11 halves, and that's going to be a plus or minus 90. So the real interesting part, challenging, tricky part about this activity is simply just the computation of all of the different angles. So one of the important takeaway messages from this, and we saw this in one of the examples that we went through, is the fact that when you're looking at either the arrival or departure angles of poles or zeros that are on the real axis, the angles from these complex conjugate pairs are going to nicely cancel out. And so that's pretty easy to see. If you have, say, poles out here and you're looking from these to this pole, this angle here, by symmetry, is the same angle. It's the kind of complementary angle to this. So that means they're either going to cancel each other out or they're going to add up to 2 pi. And so for that reason, you're not going to, so again, let me say that again. So this right here is going to be compared to this angle right here. And so that's why they're going to add up to either 2 pi or cancel out to 0. So what's nice about that is that you can just pay attention to the poles and zeros that are. If you're dealing with these that are on the real axis, like these 4, then that means that all you have to do is pay attention to these angles. And so like what we did before, we can analyze the departure angles. In this case, departure angles out of the poles at 0 at the origin are going to be plus or minus 90. We already know that it's going to be on the real axis here, so we already know the arrival angle and the departure angle here. So none of that is too new. The good thing to practice about this particular activity and this particular loop transfer function is the computation of the angles. And so it gets a little bit messy, but it's worth going through because it really clarifies how you evaluate these things. And so it's really just basic trigonometry. So we're just going to be looking at the angles from all of these other poles and zeros. And in this case, let's take a look at the example of looking at number 4 here. So in that case, we're going to first evaluate the angles from all of the zeros, and we're going to add those up. And so that's what this first bracket here is all about. So if we look at this angle is the angle at which this 0 looks up at 4. And so the basic trig that we can use is simply just the opposite over adjacent leg using the arctangent or inverse tangent. And in this case, this is 6.6 on this leg, and this is the distance between -1 and -0.1, so that'd be -0.9, and so that gives us 6.6 over 0.9 with that inverse tangent. And so that is exactly where we get this term. If we look at the other zeros, they're the complex zeros. So in this case, this 0 just beneath it looks up at an angle of exactly 90 degrees. And the complex conjugate 0 also looks up at an angle of 90 degrees to look at the pole that we're interested in. Then we're going to take a look at all the angles with respect to all of the other poles. So in that case, again, we're just using basic trig. Same logic here. Now the triangle looks like this. And in this case, this bottom leg is now 11.9, and this opposite leg is still 6.6. And so that's where we get this term right here. We can then look at the poles at the origin. So at the origin, one way to think about this is we can actually look at this angle here and then subtract it away from the whole 180. And so that's what I'm doing here, 180, and I'm subtracting away now the inverse tangent of this distance as the adjacent leg, which again is 6.6, and the horizontal leg here is 0.1. And so again, we just get this value, and this value is 6.6, and so that's where we get these two terms because we have 2 of those poles. We also have the pole that's down here, that it's complex conjugate, and it also looks up at an angle of 90 degrees, which is where that comes from. And so when you take all of that together, sum it all up, you get an angle that looks something like this. Again, it's a kind of interesting, non-trivial degree there. And so what that's really telling us is what is the angle at which this departs. And so what this is telling us is that it's not heading out this direction. It's actually heading out at an angle of 142, so that's somewhere between vertical and to the left. So it's heading out something like that. So that's the direction at which that's heading out. So using similar ideas, we can also calculate the arrival angle at this 0. And so we can get this kind of non-standard angle. And again, that's telling us that if this is 180 degrees, this is entering in just a little bit below that. And so this is exiting out a little bit above the horizontal and then coming back in like this. And so this helps us understand that, for example, this is not heading out this way and not going to potentially, as you increase k, to lead to unstable behavior because you would have crossed into the right half plane. So this departure and arrival angles kind of helps us at least intuitively understand that this kind of root locus isn't going to cause stability issues as you change k. And so now that we've calculated all those angles, again, this is similar to the examples that we saw before, where we had this value where you're essentially going to have this complex conjugate entry back onto the real axis. And this is going to head in that way, and these are going to meet and then emerge along these asymptotes that we discovered before. So just to get a clearer picture, this is the one that comes out of the one of the textbooks of this problem, just so you can kind of see it in a different scale. I definitely suggest that you go ahead and try to plug all of these in to MATLAB and see what they look like.